So welcome all to week 2 tutorial for the course Deep Learning. I'm Pintu Kumar. I'm a PhD scholar at IU or IIT Bombay. So today what I plan to cover is based on week 2 content of the course Deep Learning. So the topics that will be covered today are some basics of supervised learning. Okay. Then we'll go for a gradient descent method, which is an integral part of machine learning techniques these days. Okay. And the last one is okay, so we will then go for multi-layer perceptron. We'll also try uh, looking at sigmoid activation function and what is sigmoid neuron. I hope my voice is audible to everyone.
Yes, sir.
Okay, thank you. So yeah, and then we'll solve some questions based on this week I don't have a coding session. That will have most probably in the next week when we have covered yes, these sessions are getting recorded. When we have covered multi-layer perceptron in more depth, then I'll try to code something for you guys. Today we won't have. I'll just give one more try and try to connect Meet from my mobile so that I can see the chats. Just give me a minute. I'll try to reduce the sound. Just give me a second. Is there any echo in? Yeah, there is. Uh, is there still some echo?
No, sir.
No, sir.
Okay, I'll try to place it far away so that there is no echo. Otherwise, yeah, I don't see any other options. Okay. So yeah, I will now be able to see even the chats. So you guys can even type it in the chat box. Okay. So we'll begin with supervised learning setup. So uh, basically, in real world, what you'll encounter, you will be given with some data set, and people will ask you to learn out of this data set. Okay. So in supervised setup, the data set that is available with you is of form xi comma yi, where xi is known as feature and your yi's are called label or the values that you want to predict. Okay. So in real world, this is the setup that you will have. You will have some data set and people will ask you to learn out of it. Okay. So what is the first step that you should do when you are provided with some data set? So, okay. So just a second. So let's say you are provided with some data set xi comma yi. Here one thing is that this xi is some vector from Rn. So xi would mean that you have some features. For example, last time we did an example where you have a resume as an input or a CV as an input, and you want to decide whether you want to hire that person or not. So features would look something like their name, their age, their education qualification. Okay. So if you bundle all of them in form of a vector, this represents your xi, and your yi is your decision where you want to hire him or not. Okay. So you have many previous data points that you have collected in from your past experiences, and now based on this you want to automate this process of hiring of someone. Okay. So whenever, let's say, you are given with some set xi comma yi, the first step that you do is you bifurcate this data set into three parts. Okay. First data, anybody who has done a machine learning course would know this. I'm just covering this for others. So first part is called train split. these sessions are recorded. You will get the videos from the course page. Okay. So yeah. So first split is called the train split. Second split is something that is known as validation split. Okay. And the last split is something that is called as test split. Okay. So you should keep most of your data in your training split. That is, let's say around 80% of data. This is up to you to decide how much you want to train your model on. But for say a good way can be 60 20 20 or 80 10 10. And validation set is used for tuning hyperparameters. We'll get to it what it is. Okay. And this you can keep something around 10%. And the final testing is done on the test split, which is again around 10% of your data set. Okay. So yeah. So this is basic of your supervised learning setup. Now the thing is, like, if you have your training data set, I said that you learn on training data set. Okay. So how do you learn on this training data set? That we are going to cover, and that would lead us to something called as gradient descent method today. Okay. So as covered in the last lecture, the supervised learning setup can be further classified into two. One is classification and another is regression. Okay. In classification, your yi's are discrete, and in regression, your yi's are continuous in nature. Okay. Okay. So last week we saw that that perceptron can learn a linear classifier for any linearly separable data set. Okay, but what you encounter in real life is something that is not linearly separable data set. So data set that you will encounter in real life are generally not linearly separable. Okay. Further, these not linearly separable data sets can be classified into two categories. Okay. So one is where your data set is separable, but that can't be separated by a linear classifier. So if you have a classifier, something of this sort that I'm drawing right now, you can separate your data sets between two classes, but the classifier is not linear. Okay. So for these kind of data sets, you use non-linear classifiers, and deep learning is a very good way to learn nonlinear classifiers. Second one is, like, if you look at this particular cross mark or these three circles, these may or may not belong to that particular set where our data set is suggesting that it should belong. So these might be some errors that were made while collecting your data set. Okay, or these might be outliers. It, even if it is not error, these might be your outliers. Okay, so in this setup, what we want is, we want to learn a classifier which don't bother about these few data points, but it classifies most of them correctly. Okay, so to quantify this, what we do is, we define something that is called as loss or error. Okay, loss or error on our training data set. This will be defined on our training data set. Okay, so let's say loss is defined so that you count number of errors made. Okay, for example, in the outlier case, here you have made 4 errors, so your loss would be 4, and just to compare two different losses, we can divide it by total number of data points that we have. Okay, so the loss can be 4 by n. Okay, this loss function that I have defined just now, this is very intuitive, and this loss function is have a name also, and this is called as 0 1 loss function. Okay, you might have heard about it. This is known as 0, 1 loss function. Okay. So what it is? So you take summation of L of xi comma, sorry. So this would be loss between L of uh, f of xi comma y. Somebody typed. BN Jana, if you go to the course web page, at the bottom there is a option called a problem solving session. If you click on that, you will get all the recorded sessions. Okay. So yeah. So this is summation over all of these. So L of xi. Okay. L of f of xi and yi is defined nothing but this is 1. If my f of xi, so the value that I'm predicting for xi is not equal to what my original value is, then my loss should add 1. You can just normalize it by 1 by n, where n is your number of total training data points, okay, and 0 otherwise. So if you just add them, you will get something that is known as 0, 1 loss function. Okay. So another this was for classification. Another very common loss function for regression is mean squared error. MSE is mean squared error. This is nothing but this is normalization summation of f of xi minus yi square. Okay, this is something that is called as mean square error. Okay, so again we'll just go back to where we started. So let's say that we have sorry, we had some training set. Now for that particular training set, initially you don't know what line will separate your data point or what curve will separate your data point. What you will do is you will take some arbitrary values for your weights. Okay, so you will take some arbitrary values for your weights. For example, if you want to separate them by a linear classifier, then a linear classifier looks something like ax plus b. So you will take some arbitrary values for your a and b. Okay, and then what you will do is uh, you will try to update your a and b in such a manner that your loss function decreases in the next iteration. Okay, so let's say this is L naught, so you want your L1 to be better than L naught, and so on, and hope that you convert somewhere. Okay, so this was example for a linear classifier. In same way, you can also define some non-linear classifier like bx plus c. Here you have to learn about three quantities. Okay, a, b, and c. This is some quadratic classifier. Okay, so these were whatever I discussed till now, some basic stuff from your previous machine learning course. But I thought that this was important before we go into gradient descent, so that you know what we are doing. So in gradient descent, what we are doing is we are trying to update our values for a, b, and c so that we find an optimal separating hyperplane. Okay, any doubt till this point, whatever I have discussed?
Sir, I have one small doubt.
Please.
Is there is any difference between mean squared error and squared error loss?
Okay, so a mean squared error is that we have just normalized it. If we don't normalize it, that is called squared error. Mean is because of the term 1 by n. So we are dividing by n. That's why it is called mean squared error.
Okay, thank you, sir.
Okay, so now for some next 10-15 minutes, we won't talk about deep learning or machine learning. We'll just talk about pure maths and what is our gradient descent method. Today, if you look, like most of the algorithm, if you train, you would be using gradient descent somewhere or the other. So it is very sort of important to see what gradient descent method is. Okay. So before we talk about gradient descent, first let's look what a gradient is. Okay. So what is the motivation behind it? I'll just take a few minutes. So let's say you have a function of this sort. Okay. I should have used a different color. I'll use, yeah. Let's say this is your function and you're standing at this point right now. So you want to minimize this function. Let's say this is f of x and somebody gave you this as your initial guess. Okay. And you don't have like many information about this function and he's asking you to minimize this function. One very simple approach that one can take is, so from here he has two directions to go. Sorry, one is this direction, one is this direction. Okay, so if I move in the direction where the function value is decreasing, then I can hope that I'll reach some local minimum point at least. Okay, so what he can do is he can take a small step in the direction where the function is decreasing. Again, at this point, he will look whether I should move towards the right or the left, and then he'll reach to some other point, and so on. He can hope that he'll reach some minimum point. Okay. Now, the question is, standing at this point, how can one decide whether which direction he should move in? Okay. So if you remember, there was a like if elementary calculus. So if my f dash x at some point is greater than 0, that means that function is increasing. That means if I move towards the right from this point, then my function value would increase. Okay. So if at any point f dash x is greater than 0, you should move in left direction if you want to minimize your function. Okay. And like if f dash x is less than 0, then the function is decreasing and you should move towards right. Okay. So you should move in right direction. This was for 2D case, right? But when we look at deep learning problems or machine learning problems, the feature vector that we get or the number of parameters that we want to learn is not one dimensional. They are in terms of thousands, and even in some application you can get higher number of features. Okay. So this one dimensional calculus won't work for us, but we need to extend this notion of increasing and decreasing uh, like to higher dimension. Okay. Also, one thing is that if you were looking at a just a second, if we have a real number line, okay. So if you are standing at some point, let's say x naught, then you have only two possible directions to move from here. You can either move towards the right or you can move towards the left. Okay. Now, if you have let's say a two-dimensional plane, okay, then if you are standing, let's say at this point, then you have infinitely many directions to move in. You can move here, you can move here, you can move here, you can move here. So now you have to choose from infinitely many directions, that if you are at a point, in which direction you want to go. Okay. So towards that, we have something that is called as gradient. Okay. So if f is a function from Rn to R, that means it has n inputs and it outputs only one value. Okay. So gradient can be defined only for such function which has n inputs and outputs only one value. Okay. So function would look something like it is a function of x1, x2, xn is equal to some y. Okay. Then the gradient of that function is a vector in which first term is partial derivative of f with respect to the first variable, that is x1. Okay. And similarly, it is del f by del x2. And so on, you can define a gradient vector. This is the definition of a gradient vector. Okay. So how is this gradient vector useful? So this gradient vector, okay, so just a second. Yeah. So if you have a gradient vector, one thing that I didn't mention here and probably was not done in the class also. So if you are given with some direction u, okay, so if you are, let's say, given with some direction u, and if somebody is asking you what is the derivative of f in direction u, that means like if you are at this point in direction u, if you shift, what is the like change in the value of your function, okay. So this directional derivative in direction u can be given by gradient of f dot product with u vector, okay. So here when we talked about derivative in one dimension, then f dash x served our purpose that if f dash x is greater than 0, we should move in this direction. If f dash x is less than 0, we will move in this direction. But when we come to two dimension or higher dimension, we should find a derivative in every direction, directional derivative that is called, and then decide in which direction one should move, okay. This is why gradient is this useful. We'll get back to what is gradient descent method, but right now just remember that this is called directional derivative, and to calculate directional derivative, uh, this is very important, okay. Okay, so we'll do one or two quick questions on gradient, and then we can come back to this directional derivative notion, okay, because these are tutorial sessions, so I want to cover some questions too, okay. So I'll solve first question, you can try the other two. So let's say f of xy is given as x square y. So now this f is dependent on two variables, okay. So the gradient of f will have two components. First one would be the partial derivative of f with respect to x. Second would be partial derivative of f with respect to y. And this is given by, so if you take partial derivative of x square y with respect to x, so you should just treat y as your constant and take derivative of x square, and it is nothing but 2xy, right. And again, if you are going the other way around, you treat x square, any term that involves x as constant, and then you take its derivative with respect to y, so this would be x square. Now they have asked us to find this gradient at a specific point, that is 3 comma 2. So we will put in value over here. So the gradient of f at 3 comma 2. So we will put 3 in x and 2 in y. So this is 2 times 3 times 2, and this is 3 square. So this is 12 and 9. So this is how we can find gradient of a function. Okay. Yeah. Can you guys try for this particular function? So my f of xy is given as x plus 3y square. I'll wait for a couple of minutes. Can you please type?
So the value of x and y.
So right now we don't have to calculate at some point, but we want a generic form for gradient. Okay, so yeah.
Dou f by dou x is 1, and dou f by dou y is 6y.
Yeah, so correct. So we will first take del f by del x, and then we will take del f by del y. Yeah, somebody typed also. So yeah, this would be 1, and the other part would be 6y. This was pretty easy. Similarly, you guys can try at home for this function. These are not dependent on each other. So this is sine x multiplied by e to the power y multiplied by ln z. So you can just treat everything else as constant. So you will get something like cos x into e to the power y into ln z. Then e to the power y would be e to the power y only. So this would be the second term. Third term will have 1 by z and the first two terms as it is. You can try this thing. Okay. Okay. So any doubt till this point, then we'll move ahead. I just tried to give you a basic idea what gradient is. Okay. So, Professor Mitesh,
Sir,
yeah.
could you do it for one more iteration?
For one more, okay. So we will do gradient descent after some time. Right now we are just finding gradient. We will do multiple iterations in upcoming questions.
Okay, sir. Okay. Okay, thank you.
Okay. So Professor Mitesh, who is teaching this course, approached the proof that. Okay. So I have couple of statements to make. First statement is, like, if you take the direction of gradient of f. Okay. So if you take directional derivative in the direction of gradient of f, that particular direction is the direction in which the function increase is maximum. Okay. So if you talk about 2D, so at any point there would be a direction in which your function is increasing, there would be a direction in which your function is decreasing. Okay, this is the only two possible cases. But when we talk about higher dimension, there would be some direction in which function would be increasing, there would be some in which it is decreasing, and among them also there would be some direction in which the function increases maximum. Okay, so that particular direction is given by del of f. This is the direction in which function increases maximum. Okay, second thing is, like, in negative direction of gradient of f, in this direction your function will decrease maximum. Okay, so we wanted our loss function to decrease. So what we will do is, if we have started from some random point, we will move in direction negative of gradient of f. Okay, and we will reach to some other point. Okay. Okay, so we'll try to see why this thing works. I just want you to trust that this formula that I have written for directional derivative is correct. Okay, so if we just expand this thing, this would be norm of gradient of f into norm of u and some cos theta, that is the angle between the gradient and the u. Okay, now these two things are positive and we want to sort of maximize this thing. Okay, now again one more thing, the u, we can assume this to be unit vector because we are just talking about directions. So all the directions can be represented by unit vector only. So this norm u, if you want, let's say if you want to increase this directional derivative, norm u won't contribute to that, grad f won't contribute to that. The only thing that we can tweak or optimize is our cos theta. So when is cos theta maximum? When your theta is equal to 0 degree. Okay, so we will get maximum value when theta is equal to 0. So theta is angle between gradient of f and gradient of u. So what is the vector that has 0 degree angle with gradient of f? It is gradient of f itself, right? And we'll get minimum value for this thing when your theta is 180 degree, and that happens, so my u becomes minus gradient of f. So this is another simple proof that negative direction of gradient leads to maximum decrease in value of f. Okay. Okay. So okay. So we will try to write the gradient descent method. So you were given with some data points. So this is sort of a recap. So you are given with some data set. From here you obtain your train split. Okay. You define some loss function on this train split and you want to optimize this loss function. Okay. So what you will do is, so let's say you choose W naught randomly. So W naught is a vector consisting of all your weights. For example, if your class of classifier is linear, then your W naught would look something like A naught B naught. Okay, so you take some random W naught and then you update W1 to be W naught minus some eta times gradient of F at W naught. Okay, and this eta is something that is called as step size, and this is an hyperparameter. Okay, so after solving some examples, we'll try to see how does this step size play a role in learning. We will see to it, right? Yeah, one thing, like if you try to implement this for your deep learning models, there are many components involved in your W1 or W0. But the good thing is that you don't need to do anything from your hand. You just need to write a code and all this gradient computation, everything would be taken care of. Most probably in the next session, we'll have that thing. Okay. Okay. We can try this example. Somebody was asking to solve for multiple iterates. Although this is an function only in one variable, I thought that this might give you a lot of intuition for somebody who has not understood till this point. Okay. Okay. So my f of x, now f is a function of only one variable. This is x cube minus 3x square plus 2. So what would be my gradient of f? Gradient of f would be del f by del x. This would be only one component. Okay. So this is nothing but 3x square minus 6x. This is my gradient. Okay. Now the next thing that I'm given is that I have to calculate this till 3 iterations. Learning rate, that is my eta, is given to be 0.1, and initial value is x is equal to 4. Okay. So okay, so starting from, so W naught is given to be 4. We want to obtain W1. This is W naught minus eta times grad of f at W naught. This is nothing but 4 minus eta is given to be 0.1. I'll request you guys to please do computation. So this would be 3 into 4 square is 16 minus 6 4. Okay, so this is 4 minus 0.1 into, this is 48 minus 24. This is 4 minus 0.1 into 24, that is 4 minus 2.4, and this is 1.6. This is one iteration that we have done. Okay. Can you guys try second iteration? You can use the calculator definitely and tell me what is the value of W2. You guys can type it in the chat box. I'll wait for some time. So this would be 1.6 minus 0.1 times gradient at this point now. So this is 3 into 1.6 square minus 6 into 1.6. Yeah, a little bit of maths, but we'll get back to deep learning part very soon.
It's minus 1.92.
The overall value you are getting minus 1.92.
Not overall value, the gradient at 1.6. If I substitute 1.6,
so just a second. So if you are getting minus 1.92, then if you multiply with 0.1, this would be plus 0.192, right?
yes. Yes.
Okay. Others, can you please verify? That's why I've written it with a different color so that it can be verified. So then it would be 1.792. I'll also calculate. I'm purposely going slow, sort of in first 2 weeks. Later on, we'll try to pace up a bit. I think the professor is also following the same tactic. That's why he has covered not much content in first 2 weeks, and he is covering every basic that is required for our later on lectures, so that we don't have any confusion about these basic terms when we go ahead in our lectures. Okay. So yeah. So somebody typed yes. So I hope that is correct. Okay, so so they asked us to solve for 3 iterations. Can someone please solve for W3 also? This would be 1.792 minus 0.1 times whatever value of gradient you get. So this would be 3 into 1.792 square minus 6 into 1.792. I'll also use the calculator. So this is 3 into 2 into 1.792. I think this value I'm getting as minus 1.1182. I might be wrong also. So this is 1.792 plus 0.11182. Okay. Okay, so we have obtained something like 1.90382. Okay. So this was for just one dimension. Similarly, we can do for 2 dimension. We'll see it in the next example. Okay. Yeah. Okay. So yeah, we can probably do 2 iterations for this also, so that things are very much clear for us, like what happens in 2 dimension also, and similar thing would happen in higher dimension. Okay, so I'll hurry up here. So f of xy is given to be x minus 2 square plus x minus 3 square. So we can start from 1 comma 1. Let's take eta to be 0.1 here also. Okay, and so grad of f would look something like, okay, so there is a mistake in the question. This should be y. Sorry. Then only it makes sense. Okay. So this is 2x minus 2 and this is 2y minus 3. And most probably an easy computation. Okay. So now starting from 1 comma 1. So w naught is 1 comma 1. What is w1? This is 1 comma 1 minus of 0.1 times gradient at this point. So if you put in 1 comma 1, so this is minus 2. I might make a lot of computation mistake. Please look at it. If there is a mistake, please let me know. This is minus 4. So W1 would look something like 1 plus 0.2 is 1.2. I think I'm doing it correctly. I am doubting, but yeah, I hope I'm doing it correctly. Yeah, I'm doing it correctly, I hope. So this is 1.2 and this is 1.4. Okay. So again, this is so I'm from an operation research department, so that's why most probably I'm doing a lot of this optimization stuff. So this is 1.2, 1.4 minus 0.1 times. Now the gradient at this point would be 2 into 0.8, right, minus 0.8, that is minus 1.6, and here it would be like so 1 point, so minus 3.2. So we would reach somewhere around 0.16, right? So this would be 1.36. So, and this would be something around 1.72, right? So this is what we have got after 2 updates. Here in this example, you can see that if we can clearly see what is the minimum point for this example, right? So x is equal to 2 and y is equal to 3 is the minimum point for this particular function. Here it attains value 0, otherwise it is always positive. Okay. Now, if we would have increased the value of eta from 0.1 to 1, okay, then in the first iteration, what we would have got is, we would have got to a point something like, so this would have been 3, 5. So from 1, 1, we have even exceeded the point where we where we should have stopped. Okay, so we went beyond that point. Okay, and when we took eta value to be very small, that is 0.1, you can see that we are making very small progress, and we are taking a lot of time to converge even for this very simple problem. Okay, so what I am trying to say is, depending on this value of eta, if you take eta very small, okay, then you might miss your sorry, so if you take your eta very small, then you take a lot of time to converge. And if you take your eta to be large, very large, then there is a possibility that you don't even converge to your local minima, because you will skip that point and you can jump out of it. Okay, so one possibility is that. So you should try to take some moderate value of theta. See, like if your function is constantly decreasing, so what you could have done is, you could have checked the value of f of w naught, then you could have checked f of w naught 1. Okay, if okay, so if f of w1 was smaller than f of w naught, then you are okay. Then probably you will take more time to converge, but you will converge. You are going slow. But if it would have been other way around, let's say if f of w1 was greater than f of w naught, so that means you are doing something wrong here. So you should take theta smaller than what you have taken right now. So you should decrease the value of theta. Okay. So in machine learning training also, or deep learning training, at many points what you will see is that your loss function is decreasing till some point, and then at beyond some point it will shoot a lot. It will increase a lot and then keep on increasing. So either you should stop your training at the point where it has started increasing, or you should take a smaller value of eta beyond that point. Okay, this is one thing that you should. Okay, so this is about gradient descent. So one question that is still left unanswered is, when should we stop? Okay, so after how many iterations we should stop? Before that, any doubt in this calculation of gradient descent? Anybody has any doubt? I'll be happy to solve that. Okay, so we did 2 examples on gradient descent. Okay. Okay, so when should we stop? So in optimization, especially if you talk about deep learning methods, okay, so your loss function will always be greater than equal to 0, right? It can't be negative, right? Loss is not negative. Okay, so one thing is that if you have attained your loss to be 0 at some point, then you can stop. That means you have classified all the training points correctly. But this won't happen, like almost never it will happen. Okay, so one thing is, you can fix some bound on your loss. Let's say if you will say that if my loss becomes less than, let's say, 10 to the power minus 3, then I'll stop. Okay, this is one possibility. Another possibility is that your let's say you got wn plus 1 and wn. If the update is very small, okay, so you are not making a lot of progress, you are just stuck at some point, then you should stop your training at that point. Okay, another thing is that if your loss value that you are obtaining at subsequent points, this thing is very small, then also you should stop at some point. Okay. So these are the four things that you can think of. Okay. So yeah, one thing strike my mind that I can cover today, that is called stochastic gradient descent and batch stochastic gradient descent. But we'll get back to this towards the end if time is left. Okay. Say something about black box mystery, about artificial neural network. Okay, so okay, I'll say something. So I'll just see, when people talk about black box, so that means that your DL model or the ANN that you have mentioned is not explainable. Okay. So I'm not sure, KP Agarwal, if you have like, have you done SVM? Can I use that for motivation if you have done SVM in past, support vector machine? Okay. So this you can type like if you have done SVM in past or not. So this concept of explainability or expressibility is not very unifiedly defined right now. Okay. Okay. You have done SVM, right? So how do we like say a model is explainable or not? That is not very well like mathematically grounded. One thing that I can say right now is that when you train a deep learning model, let's say for some particular input xi, you got some output yi. Let's say you were implementing it in some medical domain, and you got that for this particular xi you got yi, and because of this prediction of yours, the patient health deteriorated. Okay, and that person is now claiming that you gave him wrong predictions. In deep learning model, there is very less possibility to tell why your model predicted yi like this. Okay, I'll give you an example from SVM. Okay, just give me a minute. I'll get back to whatever we were talking. Okay, so let's say you have two kind of data points. Okay, one is this and another one is this. Okay, now in support vector machine, your linear classifier would look something like this, and these two would be your support vectors, right? These two are the closest ones, so this would be your support vector. Now if somebody asks you like, why did you make this prediction? Okay, why did you classify this particular point to be orange rather than blue? What you can say to that person is that because this line was on right of this separating hyperplane, that's why I predicted this line to be orange. Okay, now how did you come up with this line? You know exactly that because of these two support vector points, these two data points, because of these 2 points you got this line. Okay, so you know in short that which data points, which training data points were responsible for your prediction that you made. But this kind of phenomena is not possible in deep learning models. Okay, so this is why we many a times call that this is not explainable, this is black box, this just gives us predictions, we can't interpret that predictions. Okay, so even if you want to make some small changes, if you make some small change to input, there have been phenomena that there is a drastic change in the output that is given, but we don't know the reason why our model is behaving in that way. Okay, so this is one thing. Okay, okay, so yeah, we'll proceed with the questions that we are doing. This probably would be the last thing on gradient descent today. and then we'll move to multi-layer perceptron. Okay, there are, I'm not aware of XAI that you are talking about, but there people have tried to make deep learning models explainable. One thing that I'm aware of in that direction is something called as influence functions. Okay, so what is influence function? If you have a data point xi, and so there is a some training point xi comma yi, you can tell that if I remove this particular point from training, what would be its impact on predictions of other point? This is what influence function gives you. So people have used this to quantify explainability in neural network. This thing that I'm aware of. Most probably I'm not aware of XAI. There are many new things coming up in this area these days. Okay. Okay. You can try this. I think this was ICML 2017's best paper award. Also, you can try this thing if you want, if you are really interested in this area. I think this was ICML 2017 or 2018 best paper award, and there have been a lot of follow-ups from this particular paper. So yeah, there is a term, I don't remember the title exactly, but yeah, this has something to do with influence function. If you want to know more, you can post on discussion forum. I can give you the exact link to the paper. Okay, let's look at this question. Okay, so the question is, you are training a model using gradient descent algorithm. You observe that the loss is decreasing and then increasing after each successive epoch. Okay. Okay, so which of the following technique will you use to increase the chances of convergence of the gradient descent algorithm? Okay, I mentioned it few moments ago that if your loss is decreasing, and after some point it has started increasing, then you should decrease the value of your lambda. Okay, this was a simple question from previous year's assignment. Okay, so okay, I'll talk about stochastic gradient descent and batch gradient descent towards the end. We'll move to neural networks now. That is our multi-layer perceptron, that the main core of this course. So any doubt before that about the content that we have talked so far? Okay. So till last week, we talked about a single perceptron. Okay. And we said that if our data set is linearly separable, okay, then a single perceptron is more than enough to classify this data set. Okay. Now, towards the beginning of this lecture, I talked about two kind of non-linearly separable data set that we can encounter. If we have some erroneous point or outliers, this also we talked that we can allow some error in the loss function because we want to minimize the loss function and we don't actually want this loss function go to 0. If we attain the minimum value that is possible, we are happy with it. The second problem we haven't solved till now, like how can we classify this kind of thing, or the XOR example that we saw last time. So there was a cross here and a circle here. How can we classify these kind of sets? That we haven't addressed till now, that we will address now. Okay, so what does this say is, rather than having a single perceptron, what we can do is we can have a bunch of them, okay, and connect them to each other. And how are they connected? So every neuron is connected to the neuron in the next layer. Okay, they are not connected with each other in the same layer, but they are connected to neurons in the next layer. Okay, so this way we form a network of perceptron or neurons. That's why it is called neural network or a multi-layer perceptron. Okay, so this over here is your input, the last one is your output, and the layers in between is known as hidden layers. Okay. So what will happen is that initially you will have some input. Okay, let's say this is x0, this is x1. Both these values will be passed upon to this thing and, multiplied with some weight. So this would be x0 w0 plus x1 w1, and then based on this, this perceptron will output some value. Similarly, there will be a different weight for the next perceptron. Okay, for again different weight for this perceptron, a different weight for this perceptron. So these weights that we have, so for the first layer, let's say we have 1 2 3 4 5 6 7 8 8 plus, then again this would be 16 plus 4. These weights we need to learn. And how will we learn? We will learn via gradient descent. Details we'll do in next week. There is a algorithm called back propagation that helps us calculate gradient for these complex network or multi-layer perceptron. Okay, right now we'll just do very simple thing. Okay, so what I said is that from one perceptron, now we have moved to a network of perceptron, where perceptron in the next layer is connected with perceptron in the previous layer. First layer is called the input, last layer is called output layer, and the layers in between is called hidden layer. Okay, this is what we have talked till now. Okay, now the question is, what kind of Boolean function does this network represent? Okay, so we'll see how data point is processed via these kind of network via this example. Okay, so this is a Boolean function. So Boolean function can take two inputs. Let's say this is x0, x1. Right now we are not talking about bias or threshold. We'll include it in later on. Okay, so this is the y that we want to see. Okay, so now there can be four combinations: 0 0 1 0 0 1 and 1 1. These are the four combinations that are possible. Now we want to see the values of y that we'll get. Okay, yeah, somebody is saying something. Okay, so yeah, I think so. KP Agarwal, sir, you have to say something. I think he has muted by mistake, so I'll mute him and we can proceed. Okay. Okay. So let's see, if we have x0 is equal to 0 and x1 is equal to 0, how does our data progress? Okay, this is 0, this is 0. So we had a rule in perceptron that if W transpose X is greater than equal to 0, then we output 1. If W transpose X is less than 0, then we output 0. I have changed this rule slightly. What we will do is, if it is strictly greater than 0, then we will output 1. If it is less than equal to 0, then we will output 0. Okay, this we can do. Okay, so if this is 0 comma 0, so what would be this neuron? This would be 0 times 1 plus 0 times minus 1, and the value that we will obtain is 0. Now again, here what will we do? 0 times minus 1, okay, 0 times minus 1 and 0 times 1. What we will obtain? 0 again. Okay, so because the sum that is inputted over here is 0, so it is not strictly greater than 0, so the output of this neuron will be 0 over here. Okay, the output is 0 and 0. So what is 0 times 0 plus 0? So the value 0 will get input into this, and the final output will again be 0. So the y that we obtain is 0. This is how data flows through a neural network. So for every network there will be some input, it will do some computation and it will pass on to the next layer. Okay, we'll do one more just to make sure that it is clear for everyone. Okay, so now let's say we pass 1 comma 0. Okay, so this is 1 into 1 for the top one, okay, plus 0 into minus 1. What is the value? 1. Now 1 is strictly greater than 0. So the output for this neuron should be 1. Okay. For this one, this is minus 1 into 1 plus 0 into 1. This is minus 1. So minus 1 is strictly less than equal to 0. So the output for this should be 0. Now this is 1 into 0 plus 0 into 1. The value is 1. So the output should be 1. So output of this network for the value 1 comma 0 is 1. Similarly, you can see that for 0 comma 1 it will be 1 and for 1 comma 1 it will be 0. And this is your XOR function. So we were not able to represent XOR function via a single perceptron, but via a network of perceptron we are able to represent our XOR function. Okay. Any doubt in the structure of multi-layer perceptron? How did data propagate from? So how did the forward pass happen? So if you take your data as an input and look at the like whatever values intermediate layer are getting, and you go till the output, this thing is called as forward pass. Like not very formally, but in discussions we call it as forward pass. Any doubt?
Sir, can you please repeat how in the forward pass the second neurons are getting their value 1 and 0?
Okay, so I'll tell you the rule that we have chose. So if the input to that neuron, so whatever input they will get, what they will do is, so these are the weights that I have written in orange color over here. I'm not sure if it is orange only in your screen also. So this 1, minus 1, these are the weights, and these are the values of my neurons, input neurons 1 and 0. Okay. So what will they do is, they will do W1 x1 plus W2 x2. Okay, I'll take a third case, right, and then we can see what will happen. Okay, so the input to this one is right now 0 1. Okay, now if you look at these branches, so from here we are, okay, so these two branches are going to here. Okay, so what we will do, we will do W1 comma W1 times x1. So this is 1 multiplied by 0. So the weight multiplied by the input plus now this is 1 into minus 1. What is the final value? Minus 1. Now we have a rule. What value would our perceptron output? Okay. So this minus 1 is less than equal to 0, right? So it will output 0. This is the rule that we have made. So the output of this one would be 0. Now we can again similarly look at this one. So this would be 0 times. Okay, so I can use another color. So this thing is going here. Okay, so this is 0 times minus 1 plus 1 times 1. So this is 0 plus 1 is 1. Now 1 is strictly greater than 0. So the output of this neuron would be 1. Okay, similar thing you can do for the next layer also. So this would be 0 times 1 is 0 plus 1 times 1 is 1, and 1 is strictly greater than 0. That's why the output would be 1. So the final output is 1. Whoever asked, was I able to clear your doubt? Was I clear?
Yes, sir. Thank you.
Okay. Okay, we can do this question. Okay, so we won't do this question actually, but I'll just motivate why I wrote this. So like why? So one thing is that in last class we were not able to do XOR using a single perceptron. We were not able to bifurcate XOR using a single perceptron, but we did using a network of perceptron. Okay. So the question is, so we were able to do for XOR, would we be able to do for all possible Boolean functions or not? That's the main question. If we are able to do for all Boolean functions, then only there is a hope that we should use deep learning methods to learn any functions, right? So the answer is yes. If you have one hidden layer and you allow arbitrary number of neurons in this one hidden layer, and you have output connected to it, then you can learn any arbitrary Boolean function. Okay, and that network would look something like this. That's why I wrote this network. So here also we have same rule that if W transpose X is strictly greater than 0, then my output is 1. If W transpose X is less than equal to 0, this is strict inequality, then my output is 0. Okay, so if you look at this thing, so whatever input you take, this particular quantity would sort of represent your 0, 0 case. Okay, so let's say you have some truth table where you have some x1, x2, and you have some y. Okay, then you will have 4 inputs, right? 0, 0, 1, 0, 1, 1. Oh, okay, sorry, let's make it 0, 1, and then 1, 1. Okay, you will have 4 inputs, right? And you will have some output corresponding to it. Okay, let's say I wanted to make this network for my XOR function. So the output would look something like 0, 1, 1, 0. So how can I make such a network? The easiest way is, so for every network, the first two layer would look the same. Okay, so the input layer as well as my hidden layer will be same. What will we do? For the first one, we'll choose minus and 1 and minus 1 as my weights. Okay, so this would represent 0, 0. For next one, I have minus 1, 1. So this would represent 0, 1. Next one is 1, 0. And last one is 1, 1. Now for these weights, whenever you get value 1 as your y, for those particular branch, you take 1 as the weight, and for rest you can take 0. Okay, so this way you can represent any arbitrary Boolean function using a network perceptron, and that has only one hidden layer. Okay, now if you look at this one, so this weight is 0, right, and this weight is 0. So this is not contributing anything to the output, right? This and this is not contributing anything to the output. And if you look carefully, this is very similar to what we drew in the last example. Okay, so many times it would be, there would be a possibility that some of them are not contributing. You can just remove those particular paths to get a smaller network. Okay, so any doubt in this? Okay, so there are these kind of questions in this year's assignment, so I have included few of them. Okay. So the question is, how many Boolean functions can be designed for 3 inputs? Okay, so
A, option A.
This is for 3 inputs.
3 oh, sorry.
Yeah. So this is different from this.
256. 256.
Yeah, I think that is correct, but I'll try to explain for others, like how does this happen. Won't take much long. Okay. So how can you write any arbitrary Boolean function with 3 inputs? So now there are, let's say, x1, x2, x3 are your 3 inputs. Now x1 has 2 choice, so this would look something like 1, 1, 1, 1, 0, 0, 0, 0. So this is 1, 1, 0, 0, 1, 1, 0, 0. This is 1, 0, 1, 0, 1, 0. This we have been doing from our class 12. Okay. Now for this particular position, you have 2 choices, right? Again, for this position, you have 2 choices. and you have two choices for 8 such positions. So how many functions you can define? You can define 2 to the power 8 functions. Okay. So this is 2 to the power 8 is 16, 32, 64. Yeah, this is 256, right? So if you have, let's say, n inputs, then you have 2 to the power n choices to fill, sorry, places to fill. Okay, and for every place you have two choice. So this is 2 to the power 2 to the power n that you will get. Okay, so this is, yeah, 2 to the power 2 to the power 3 is 2 to the power 8, that is 256. Okay. Okay. Okay, so this is our question. So how many neurons?
30.
I think that is correct. Yeah. How many neurons do you need to? Can you please mute yourself?
Yes, yes.
So how many neurons do you need in the hidden layer of a perceptron to learn any Boolean functions with 5 input? So you have only one hidden layer allowed. So if you look at this example, in the hidden layer, we tried to find a neuron corresponding to every possibility over here. So for 0, 0, we had one neuron here. For 1, 0, we had one neuron over here, and so on. Okay. So this was for 2 inputs. Okay. So for 2 inputs, we had 4 neurons that we wanted to do. Similarly, for 3, we had 8 choices. Okay. So we had 3 positions to fill and 2 choices for every position, right? That's why we had 8. So similarly, for 5 inputs, you will have 2 to the power 5 neurons in the hidden layer. So for n inputs, you will have 2 to the power n neurons, right? So this 32 is correct. Okay. So this is another question. Yeah, somebody typed it in the chat also. 32 is correct. Okay. So question is, there is a neural network. So that has 2 hidden layers with 5 neurons each. And the output layer has 3 neurons. Input layer has 2 neurons. How many weights are there in total to learn? Okay. So weights, so these connections will have some weights corresponding to it. Right now I have explicitly written the weights, but in practice these weights won't be available to you. These are the weights that you need to learn so that your data fits well. Okay, so we can draw this network. So input has 2 neurons, second layer has 5, 3, 4, 5. This also has 5, and the output has 3 neurons. So there will be a connection from everywhere to everywhere. Okay. Right now, just assume that there will be connections from everywhere to everywhere. Later on, we'll see that we can skip some connections. Okay. So we need not draw the complete neuron. So from the first input, there are connection going on to 5 neurons. Similarly, from the second, we have connections to 5 neurons. So here we have 2 into 5 weights that we need to learn, or there are 2 into 5 connections. Here each 5 will have 5 connections. So here we will have 5 into 5 connections or weights to learn. So we will have, for example, for this, these are the 5 connections. For next again, we will have 5 connections. The picture would look very messy, that's why I'm not drawing further. Okay. Okay, let me draw. Okay. Okay. So it would look something like this. And again, from here we have 5 cross 3. So we can draw similarly, right? So the total number of connection is 10 plus 25 plus 15, that is 50. So you need to learn 50 parameters. Now this is a very small kind of model. We don't have many neurons in the intermediate layers, or we don't have many number of layers. Still you have 50 parameters to learn, and this can motivate you to see, like, uh, doing it via hand or even using low compute resources are not very helpful for deep learning model. That's why with the advancement of computation, this deep learning models have re-evolved, like after this AI winter that people say. Okay, so yeah, this was about introduction to uh, multi-layer perceptron. Now we will look something that is known as sigmoid neuron and solve a couple of questions based on it. Okay. If you have doubt, you can anytime unmute yourself and speak, or you can type. Is there any thumb rule on number of hidden layers and no, there is no thumb rule for that. So, like, most of the time it would depend on your application and things that you're doing. One thing that you can do is, so we had a validation set. You can use validation set to tune in your number of hidden layers and number of uh, uh, neurons in a particular layer. So there is no thumb rule as such, but one thing that I can say from experience is that for applications related to images and your normal so Euclidean feature, Euclidean data. Okay, so people have shown that the deeper they have gone, the more layers that they have used, more number of neurons that they have used, they have got better results. Okay, but that again depends on your compute power that you have, the kind of machines that you're using. And another thing is, for some recent methods have been proposed. You might have heard of something called as graph neural network. Okay, these are being used in many applications these days. So GCNs, etc. They have a problem. If you go very deep or if you go very broad, then they suffer something that is known as over smoothing, or so this is a bottleneck that is known for GCNs. So for these kind of models, you should avoid going large and deep. Okay, so this is one comment that I can make. Otherwise, you should use your validation data set to tune your width. So most of the work is going on in this direction only. So how can we get the optimal, yeah, accuracy that we want? Okay. Okay. So yeah. So this is sigmoid neuron, but there can be many similar neurons. So I'll just give you a brief motivation. So right now what we were doing, for every perceptron, we had some input. So let's say this is W1, W2, W3, W4, and this is X1, X2, X3, X4, this is Y. So if my W transpose X was greater than equal to 0, then we had some rule, and if my W transpose X is less than 0, then we had some rule. If you look at this, these conditions are still linear, right? If we want to make these conditions non-linear, what we can do is, we can pass these values, whatever we have obtained, let's say W transpose X, via some function, and make rules based on now the f or phi of that particular W transpose X. Okay. Okay. So this is introducing non-linearity. One such possible function is something that is known as sigmoid function. Okay. So sigmoid function is generally represented by this sigma, and sigma of x is given by 1 upon this is 1, not 11. This is, okay, sorry. This is 1 upon 1 plus e to the power minus x. Yeah, this will be covered not today, but in subsequent lectures. This is just introduction to multi-layer perceptron today. So this is a 12-week long course. We will definitely cover specific activations functions and their applicability. Most probably next week we'll cover, or maybe week after that. Okay. So yeah, this is something that is known as sigmoid function. So this is generally used for classification purpose for two reasons. So if you remember this is the graph for this sigmoid function that I just said. If this is your x and this is your sigma of x. Okay. So if you look at your 0, 1 loss function, so till your input, yeah, that is W transpose x is greater than 0, this is 1. And for other part it is 0. And there is a sharp increase here or decrease here based on the inequality that you're using. Okay. So if you look at this sigma function, this is a very well approximation to your step function. Okay. But this step function of yours is not differentiable. In fact, it is not it is not continuous at this point, right? So we approximate it via a more smooth function so that we can find its gradient and those kind of things. Okay. So this is one motivation for using this sigmoid activation. So earlier what we were doing is that if our W transpose x is greater than equal to 0, right, then we will predict 1. Okay. Now what we will do is we will just pass this W transpose x via sigma, and that will be our output. We need not threshold that, we need not check whether it is greater than equal to 0 or not. We will just pass this thing via this sigma, and that will be the output of your neuron. Okay. Now y is just your activation, this sigma of W transpose x plus b, if you include the bias also. Okay. So this is how a sigmoid neuron looks like. So earlier you had a case that W transpose x is greater than equal to 0, then you should get 1. Now if you look carefully for very small values, you will reach this thing, that if your this is not exactly, just a second, 1, but your 1 is somewhere over here. Yeah, this is your 1. Okay. So sigma of W transpose x will itself output some value very close to 1 when your x is greater than equal to 0. Let's say it is 0.4 or something like that. And if it is negative, it will automatically push it to 0. But it is a smoother version of that. Okay. And this is how it looks. There are other similar functions.
Excuse me, sir.
Yes.
Can you please tell this on the x-axis, this point is B or minus B, the center point?
Can you please, so this over here?
Yeah.
So this point is 0 over here.
0.
This is 0.
0 means B is 0.
Yeah, right now, okay, so yeah, I got your question. So right now over here I have just plotted phi of x, that is 1 plus 1 e to the power minus x. So this point right now over here is 0 only.
Yeah, if you take it as z, e raised to power minus z.
As 0, so what we want is that our W transpose x plus b should be 0.
Yeah.
Right. So this would be, okay, so when your W transpose x is equal to minus b, so this point would be minus b then.
Minus b, okay, fine. Take it, right, thank you.
Okay, so yeah, this is how a sigmoid neuron works. Okay, so when we were talking about multi-layered perceptron, Okay, so we said that it can approximate any Boolean function. Now what I'm saying is, if you replace your these simple perceptrons by sigmoid perceptrons, then just by one hidden layer, and if you allow large number of neurons in that particular layer, you can approximate any function to desired accuracy, and this is called universal approximation theorem. Proof has been discussed very beautifully in the main course lecture, so I won't repeat that. Okay. That's not a proof actually, but the motivation that is very well motivated over here. So I'm just mentioning over here that if you replace this thing, then you can very well approximate this thing. Okay. Okay, so we will do some questions based on the sigmoid neurons. Any doubt if anyone has related to sigmoid neurons, that person can ask.
If we talk about perceptron, that means in perceptron we have a step function as our output, right?
Right. Right now, we are talking about that only. But if we talk in real world, then we loosely use a perceptron as any like this kind of structure along with some activation function, right? Right now, we have
Right.
just learned about the sigmoid activation. So
Only
in this
one.
course,
Yeah.
the pattern that we are following, perceptron means that we are just interested in W transpose X and not this function right now. But loosely
And
speaking,
this is also perceptron, na? If
this is
we
also a
do not have
perceptron.
any hidden layer,
If we don't have any
then
activation function,
this is also a kind of perceptron. No doubt, activation is just sigmoid. We can call it as a perceptron model.
yes, we can also call it as perceptron. People call it as perceptron, but because in this course perceptron was specifically defined by the prof, so I'm sticking to the perceptron for that thing only.
Okay.
Okay. So
ठीक है.
right, the course that I did there also we loosely called everything as perceptron. So any of this kind of structure along with the activation function as perceptron. Okay. So yeah, that's just the notation that we should pick. There is nothing logical over there, right? So yeah, this is a question. Okay, so the question is that we have a classification problem with labels 0 and 1. We train a logistic model. So logistic model is just logistic is sigmoid to just consider for right now, and found out that W node learned is minus 15. Okay, so we had W transpose X plus B. So now B, they are using W naught for B, and that they have learned to be minus 15. We have to predict the label for a new test point X. Okay, and for that W transpose X is 1. Which of the following is true? Okay, so yeah, so this is a logistic model. So we want to do sigmoid of 1 minus 15, that is sigmoid of minus 14, and you will predict the label to be 0, because you will get very small value close to 0 from here, you will not get 0, but when you get very close value close to 0, you predict your label to be 0. This is what happens. Okay. Okay, so here I have a different question. This was there in last year's assignment, but I don't think professor has discussed about this right now, but I'll briefly say, okay. Right now, the classification problem that we are dealing with is called binary classification, because right now whatever examples he has motivated or we have talked about has only two possible outputs, whether it should be 0 or 1. Okay, but that's not always the case, right? For example, let's consider this example where you have photos of people wearing some clothes and you want to predict what kind of cloth it is. Okay, this is a very much real world application. So in that you don't have only two choices, but you have four choices to choose from. So whether it is a hat, whether it is a t-shirt, whether it is a jeans, or whether it is a scarf. So you have four choices. Okay, so this kind of setup is called multi-class classification. From binary, we have moved to multi-class classification. Okay, and multi-class classification also have two different categories, loosely speaking. Okay, this is multi-class. Okay, so somebody has typed something, I guess. Sure, Himanshi, I'll discuss. After this question, I'll discuss. Okay. Okay, so yeah. So there are two different categories when you have more than two labels. One is called multi-class and one is called multi-label. Okay. So I'll give you example for both to motivate. So let's say you have pictures of animals and you want to predict what kind of animal it is, whether it is a cat or a dog or a lion or a tiger. So for every picture, you will have a unique label. Okay. A same animal can't be cat and a dog both at the same time, right? So when you have a unique label, that kind of setup is called multi-class classification. Okay. Another possibility is in the same image you have both let's say cat and dog present over there. Then the output would have both cat and dog. Okay. So for example, in this case, the person is wearing hat as well as t-shirt. So the output should be hat and t-shirt. Okay. So these kind of setup is called multi-label classification. So there are multiple labels associated with same example. Okay. So how do we extend our neural network to learn this kind of setup is, there was a question, that's why I am doing this thing. Okay. So right now, let's say this is your input. These are three hidden, yeah. And you have three classes from which you want to predict. Okay. So now your output layer won't have just one neuron, but three neurons. Okay. So first neuron would say whether, let's say if you take this example only, hat, t-shirt and jeans. So value of this neuron will tell you whether like hat is present or not. Okay. The second output neuron will tell you whether t-shirt is present or not. And third neuron will tell you whether jeans is present or not. Okay. And we'll go to this in next class, but I'll just tell you one thing. Here, the output won't be much like 0 and 1 that you will get in the final layer. You will get probabilities between 0 and 1. Okay, sir, do we get pre-recorded? Yeah, you will get these sessions recorded. I'll upload it in half an hour or so after the session ends. Okay. So you won't get exact 0 and 1 values, but you will get some probabilities between 0 and 1. Why would that happen? We will talk about it in the next class. But right now just know that like we will have multiple neurons in the output layer, and those values would be some probabilities between 0 and 1. Okay, so if your probability is more than 0.5, then you can predict that that particular thing exists in that image. Okay, now let's get back to the example and the things would be more clear. So the example says the output layer of sigmoid neuron has following values. Okay. So there are 5 output layers. Okay. And the outputs are 0.9, 0.1, 0.49, 0.63 and 0.33. Okay. So what should be the predictions that you make if you have these kind of outputs? As I said, if the output is more than 0.5, you should make prediction 1. Okay. If the output is less than 0.5, you should make prediction 0. So this example is option is correct because I have made prediction 1 for 0.9 and 0.63 and 0 for others. Even if you don't understand this right now, it's fine. We'll cover it in more detail in next week lecture. Okay. Okay. Okay, so for this sigmoid problem, Himanshi will get back to this towards the end. Let's look at the other question also so that others are also involved. We'll definitely do this question, but towards the end. Okay. So the question is, what are the advantage of sigmoid decision function over the perceptron 0, 1 decision function? I mentioned that the perceptron is continuous and differentiable at every point. So that's why this option is correct. Okay. What is the range of this sigmoid function? This is the question. So we have drawn it over here. The values lies between 0 to 1. This is 0 and 1. So the values lies between 0 to 1, and it never attains 0. So this second one is the correct option. So they will never attain 0 and 1. That this is also that you, this option is incorrect. So value very close to 0 and very close to 1 is the answer. Okay. Okay. So yeah, now I can get back to Himanshi's question. Okay. So what happens in a sigmoid is that we want to output the value of sigmoid of W transpose X plus W naught. This is what we want to do. Now W transpose X is given to be 1 for us, and W naught is given to be minus 15 for us. Okay. So what is the value that we want to predict? This is sigmoid of minus 14. Now I just drew the graph of this sigmoid function but didn't tell you exactly what happens. So for sigmoid function, if you have 0, you get half. If you have some positive values, let's say x greater than 0, then you get values close to 1. Okay. If you have x less than 0, then you get values close to 0. Okay. So you see that it very sharply falls below, right? Very close to 0. So this is just minus 3 over here, right? And this is just 3 over here, and it has got very close to 1 and 0. So when we have minus 14, the value that we'll get will be very close to 0, right? So we would be making label 0 as the prediction for X. Was I clear, Himanshi? Okay. So we have some time left. I'll take 5 minutes to introduce something that is called as stochastic gradient descent and batch stochastic gradient descent. Okay. So we talked about gradient descent from some mathematical perspective. Let's first talk about that from deep learning perspective. Okay. So what will happen is, so we will have, let's say, so we will have a bunch of data points, training data points with us. Let's say these are x1 to xn, x2 to, so xn to yn. We have these data points, okay, and we have some network. Let's say this is a very small network, similar to what we had, right? So this is W1, W2, W3, W4, okay, and this is, let's say, W5, W6. I am ignoring the bias for the time being. Okay, this is what we have right now. Okay, so what will happen is, so the prediction that will be made is, so for the first layer, let's say this we call as output 1, this we call as output 2. So output 1 will be W1 x1 plus W2 x2. Output 2 would be W3 x1 plus W4 x2, and the final output y will be W5 O1 plus W6 O2. I am repeating this thing again and again so that it gets in your memory. Okay, so this is how a forward pass would look like. Okay, so this is, let's not denote it by y, let's denote it by f of x, x1. Okay, f of x. Okay, so for every point we will have this kind of value. So what we will do is, we will initialize some W naught initially, and the loss function that we will have is the summation of loss at all the points. So we will have f of x1, sorry, f of xi and yi. So loss between f of xi and yi. So this x1 over here and x1 over here is slightly different. This is the component and this over here is vector. This is a abuse of notation, I'm sorry for that. Okay, so we have some of this losses. Okay, this is our loss function that we have. When you will find the gradient, so the gradient of L would look something like summation. So because the derivative you split over summation, so you will split something like this, right? I hope I made sense over here. So that the gradient would be sum of gradients of all gradients at all the points. Now let's say if you have million data points, and this is not very rare, this is common these days, you will have millions of data points. Okay, so you will take the summation over all the data points. This will make the learning process very slow. Okay, so for every update you will have to calculate lot of gradients and then take their sum and then update your parameters. Okay, so what people suggested is that you can do something that is known as mini batch gradient descent. Okay, what you can do is you can divide your training data set, let's say in 3 batches. You can divide in any arbitrary number of batches. For example, I am taking 3 batches. Okay, you can divide from x1 to y1 to x1 to sorry xk1 to yk1. Okay, then you divide it from xk plus 1 to, let's say, xm to ym, and the final split will have data points xm plus 1 to ym plus 1 from here to xn to yn. Okay, so now rather than taking the sum from beginning to the end, what people do is, so for the first update, let's say it is w naught. So what should have been the ideal situation? So ideal situation should have been, if you have w naught, then w1 should be w naught minus some eta summation I is equal to 1 to n gradient of L f of xi comma yi. Right, this should have been the ideal situation. Okay, I'll talk about the recording sessions in a while. Just please be here, I'll talk about it. Okay. Okay, now rather than doing this, what happens in mini batch gradient descent is, in the first step, what you will do is, you will do w1 is equal to w naught minus summation I from 1 to k only. Rather than taking all the points, you are not taking only first k points. Okay. So because we took a mini batch from the complete training data set, this is called as mini batch gradient descent. Now for the next update, what you will do is, you will do w2 is equal to w1 minus, now eta times, now this summation would not be from 1, the summation would be from n plus 1, sorry, k plus 1. So this is from k plus 1 to m points. So the next batch comes into the picture, and then the gradient. Okay, and again the last update you can do like this, minus eta k plus, so this is m plus 1 to n gradient of L f of xi yi, right. So you would have reached from here to here in one update, but you are splitting it into 3 updates. I would like to say that this w1 and w3 need not be same. Actually they won't be same. Okay, so yeah, this is something known as mini batch gradient descent. Okay, and this is very common because this has other advantages also, that you can skip some local minima using this method. So those things we can discuss later. One thing more, very small thing is left, that is called as stochastic gradient descent. So we talked about normal gradient descent, we talked about mini batch gradient descent, now we are talking about stochastic gradient descent. Okay. So now here also we were taking some bunch of points, right? We took a smaller set that we called as mini batch. But what we can do is we can just take one point at a time and update our W. So what would happen if we have W naught? So for W1 would be W naught minus eta times gradient of L at x1 comma y1. Okay. W2 would be W1 minus eta times gradient of L at x2 comma y2. We are just taking one point at a time. So this kind of method is called as gradient descent method. Sorry, stochastic gradient descent method. Because we are taking some random point and we are updating in that direction. Okay. Yeah, this is what I wanted to tell. Anybody has any doubt related to today's content can ask now. Otherwise, I think this is what I prepared for today. Somebody asked about recorded sessions. So yeah, I can probably share the screen and show you how you can reach there. I'll stop presenting this and I'll stop the recording.